Hello everyone, welcome back to the part 3 of the Artificial Intelligence at the beginners level program. Okay, before entering to the today's topic, I'll just do a quick recap on what we have learned in the previous session. Okay, so we started with policy and what is meant by policy and then what is the plan, right? So what is the basic differences between policy and plan, right? So we have our Bellman equation with V of S, this is value of the state is equal to maximum of the action which we get for moving to another state where I will be getting a reward for the state for the corresponding action plus gamma times, which is the discount factor of the probability or the randomness of the state and its action with its corresponding state, right? So including its value of the next state, which is v state s prime, right? So we'll move on to the next. This is what the Boltzmann equation if we just go only with deterministic search, right? So what we see here, like we just derive the value from here, then if it has a problem, like it can move here or here. So we have a deterministic search. So if it is here, it will move here. If it is here, it will move here. There is no other go, right? So this is what we call something like a plan. Okay, so what will be my diagram, something like that. My if my agent is here, it will just follow this path. If similarly my agent is here, it will follow this path, right? If it is here, it will follow this path. So this is the actual plan. This is the actual plan the agent will be following if we have only deterministic search, right? So we got the next thing. If we don't have a deterministic search, so what is a non-deterministic search? Suppose if my agent is here, consider my agent is here, it is a probability of moving something. Suppose it is here, it is a probability of moving here and then here. Even though it have a bigger value here, suppose consider to be probability of moving for 80% is here, 10% is here, it have not only one go, it have many possible outcomes, right? So it is a non-deterministic. So we cannot determine the exact move the agent is going to do, right? So we use the term non-deterministic. Okay, so moving further, we have using the Bellman equation, integrating that Markov function. We got this, right? Bellman equation, we just redefined it and we got this, right? So according to that, we just derive all the values according to it. So suppose consider to be it is here, it will move here rather than going up, it will go here. Why? Means if it goes here, it has a probability or randomness of moving to the pit. So what it does is it just move like this, right? So you can see. So if it is here, it will just try to hit here, and at most at that 1%, it will just move here. Right? So it will take a path like this. So it tried to eliminate the getting a negative reward, right? So it doesn't want itself to get into something like a bad feedback. So if it is facing like this, it have 8%, 80% of chances moving to this cell, even though it has a 20% of chance moving here too, right? So suppose consider to be 80% means if it tries for 10 times, it may go 8 times here, 2 times here. We may not sure that like that 8 moves will comes in the first. If the first move itself it is here means it will fail. It will fall into the pit, right? So what it does? So it does is like, so if it is here, it will just go back for 10 times, sorry, 8 times, and it will go here, right? right? So what next? So we are seeing it tries to eliminate, it's trying to eliminate. So what it does here, it will just move for 8 times here, and then even though if it is the 9th time, it will just move on to this and it will start moving here like this, right? So same occurs here. If it is a probability of moving up this side means it will just keep on moving this, instead of rather getting a negative feedback, it will move at any instant. It can move here, it will take this path, and here it will take this path. So this is what our policy. So this is the basic difference you can see. So this is our plan and this is our policy. So policy is nothing but it's something related to the plan, but something we don't want to, or the agent doesn't want to take any risk to get into some negative feedback, right? So moving further, we introduce the other term called penalty. So what is meant by penalty? So here you can see the thing, the agent is, if it is in this place, it tries to move here and then it cannot, it's like it takes the longest path to eliminate the probability or the randomness of falling inside a pit, right? So what it does is takes the longest path. Even that is should be eliminated, right? So we give something like the agent should be like, if we give one condition, it will take that condition and it will analyze, keeping that condition, what is my smartest way. Okay. Second, if we give another condition, it will club both condition, it will get a smarter condition out of it. Okay, suppose now I gave a condition like I have a reward +1 -1 here. So what it does is, I don't want to fall into -1, so I can take the any route which is very safe to me. So it takes this path, right? So what I'm going to do, I'm going to add some penalty. So penalty is nothing but for every move, I'm going to give some rewards. Rather, here we were giving +1 here, -1. If we move to this state or this, going to give any penalty, right? So we got the Bellman equation again, right? So as I was saying before, for every agent, for its corresponding action inside an environment, there will be a state it will be achieving, whether it is a same state or different state it will be achieving, and for achieving that state it will get some reward. Okay, so we usually, what we did is we gave two values or two rewards, right? So if it reaches here, it will get +1. If it reaches here, -1. So what it does is, I want to get into here with the safest way. So if it is here, I have three possibility. I can move up on this side, right side. So if I go like this, if I'm here, it has a probability of moving up, down, or going like this, right? So what it does is it goes in the path which is somewhat safe to that. So for that, what we are going to do is we are going to add some penalty. Okay. So suppose if it takes the longest path, it will consider, see, one, if it goes to here, -0.4, -0.4. When if it goes, it starts to compare. Okay, if at all I take a longest path, and if at all I take the probability of going this way, which is safer to me and which rewards me more, that will be its mentality. So here we have mentioned -0.04. If it is present in that, it won't come. Suppose it went to this state and comes back to this state, then it will get a reward this one. But initially, it will, reward point will be 0. Keep in mind, a reward point of agent by starting or for at the end of the, or the start of the thing will be 0. Okay, so we are going to add some more concept. Means first we said just avoid falling into the pit because it has some negative rewards. Now we are going to add some penalty for that, so that it don't want to move, or it want to compare which is the best out of two conditions. So when we gives reward to be 0, so it has nothing. So it tries to eliminate not going to this pit. So the same thing occurs. So if it is 0.4, okay, it will think, Okay, 8 times I should hit and then I should go. Better I can go like this. So I can just make a better move. And here see, instead of hitting like this, I can guess the probability of moving up. Okay, same like that. If it is 0.5, even more further, it won't take, if it is here, it won't take the longest path. It will just take the shortest path. Okay, if it is take this path, something like this, 0.5, 1, 1.5, 2, 2.5, and then 1, it is 1.5. Rather, I can take here this one to be zero point 0.5, this one to be 1, and then if I go here, same result, right? So I can, instead of that, it will just sort out the best way out of it. So if it is -2, it just say, instead of I'm going round to here, I can just fall into here, -1. That is better. If I go here, it is -2, which is too costly, a too bad reward. Right? So this is what we are asked, leaving penalty, we are penalizing everything. So we just move on to Q learning intuitions. So Q learnings are nothing but the quality of learning. So every time how it learns, that the things happens, right? So we just come again to the Boltzmann equation, right? So we have the things like the formula of Boltzmann equation to consider the value of the corresponding state, right? So if we just see about the Q, so where is the Q? So before we were just taking only the values to which the probability of moving to this state or to this state or to this state, right? So now what we are going to say? We are going to say for what action, we are going to see for what action the corresponding state will be. Okay, so this action means, let's do me this. So this action, suppose consider to be, if it is here, for moving to this side, for my this action, -1 I'll be getting. For moving to this, my reward will be minus 0.5. Okay, if I move right, so my action is moving right, so my reward is minus 0.5. If I move up, my action is moving up and reward is plus 0.5. Something like this. So it will not only it will determine the state, it also calculates the action what it is doing, so that if it bears something bad, it will try to neglect that action. Instead of going to the state and analyzing, it will just remember the action and it will try to eliminate that. Okay, so here what we have is, we have a state here. If I just move on to the here another state, I have a queue. So consider like what state and which action brings to that state, right? We have our Bellman equation. So to find out the value of that state, we have the maximum of the reward will be obtaining when we go to that state by the certain action and the probabilityness of achieving that state, right? So how we can get that quality? So it is indeed, if we move to other cell, I'll be getting appropriate reward, right? So I'll be getting a reward. Okay. Plus, I'll be getting the discount factor times of the probabilityness or the probability or the randomness of the particular move. Okay. So if I just look somewhat deeper, it is nothing but this. So I can describe the value of the state can be determined like the maximum action of the Q learning intuitions, right? So further moving, I just want to say simplify everything in the terms of Q. So I just try to substitute the value of the next, means that upcoming state. So what I'm doing is I'm just applying it here. So this will be my Boltzmann Q learning institution formula. Okay, so moving further, I just gave you some additional readings, right? So we were just dealing with some additional readings. So, so moving on, we just come to the temporal difference. So before entering into this topic, I just strongly recommend everyone to understand this concept, as this is the soul for learning the artificial intelligence. So if it is the main picture of artificial intelligence learner, then their what to say, their proceeding like future sessions will be won't be a big deal for them. Okay, so temporal difference. So what is mean by temporal difference? So temporal difference, alias, which is called as TD, in the reinforcement learning, is an approach to learn, to the agent to learn how to predict a quantity. This is something like a tool or some framework to approach to how to learn, or how to predict a quantity that depends upon the future values. Suppose if I go to that cell, what is my value? So it gives some clear cut view for the agent. Okay, if I move to this state, I have three options, and which will be the better one? Okay, so this is the thing, like the basic and the most important soul part of AI. Okay, so the name temporal difference derived from its use of changes, means you can difference in prediction over successive times to derive the learning processes. So you'll be saying, right, artificial learning is all about not the programming part, it is all about the learning by the agent every time, right? So this is what happens. So this temporal difference just compares, just says, okay, first time you went this, okay, next time it won't do that, it just compares. Okay, let's just move into that and we can just see. Okay, so we have once again the deterministic search and the non-deterministic search. So deterministic search means something like, okay, I just want to move up, that is the only way I have. So it we can be deterministic. So this is my way, and the agent will be moving this way only, not rather than any other option. So we'll left at this as of now, and we are going to non-deterministic search. Okay, so in non-deterministic search, I have many possibilities, I have many probabilities, I have many randomness. Either I can just move in this side, up, north, east, west, south, any side I can move, right? So there is a probability of moving to a certain state is somewhat higher or less than probability of moving in the other directions, right? So we have here, we just use deterministic search, means I have only one way to move, I have a deterministic way, right? So this is the exact point. Okay, so what it will be like, if it is here, it will just start moving here, 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 and then there. If it is here, somewhere here, move this here, here, here. If it is here, it will just move here, 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 and then here. Okay, so what is the next? So this is something we derived the Bellman equation using the non-deterministic search, right? So we have we find very difficulty, even though this value is derived from this value, even this value is derived from this value, right? So we have a multiple set of confusions if you want to determine the value of the state. So what we are going to do that is, as we seen this, how to determine the quality, that means Q learning intuitions is something like a reward we just saw, right? So in how to determine the Q learning intuitions, right? So this is somewhat we derived from the Bellman equation. So we'll be getting rewards and the alpha times, which is the discount factor times of this value. Okay, if it, this is for deterministic search, and if it, sorry, non-deterministic search, and if it is a deterministic search, I'll be directly going, there is not a there is no big deal in that, right? If it is something like it will move up only, okay, then my agent will go up, then next right turn, next left turn. So I don't have any confusion, then I can just determine my state value. That's not a big deal. So if the things comes when, and if in all real life scenarios, artificial intelligence will think n number of time before just moving into its another state. It will just calculate which is the better, which is the best. It will just calculate. So theoretically we can just go with deterministic search, but in practical environment only the non-deterministic search will be there. Anything, if my dog want to move, it will just give, okay, what is my function. It will just say, okay, which set of things I can do. If I do this, what is my result? What is my action? For my action in this environment, what is my reward? It will just evaluate everything, right? So you can see here, this is the factor, the maximum action we are going to get in the next step. So this value is somewhat independent on the next, what value, what state we are going to get. It is determinant of that value. You're getting that, right? So if I going to calculate, or if I go to calculate some intuitions, Q-learning intuition for a certain uh, state, I want to check which is the next preceding of mine. Okay, so I'm going back to the same maze that I have here. So suppose I'm here, so I'll be getting some rewards or something like learning when I just move to the next state. Suppose it will be having something, but I'm just not mentioning that because it's not something not relevant to that. So I'm just saying value I'll be getting. I'm not mentioning what value is that because for simplicity I'm just doing that. Okay, so we do have some value, right? So before, what was it? So before moving, it was like q of, for learning we'll be getting something for certain action, and then we'll be moving to certain state, right? So once it is done, it moves to the next state, right? So what will be, so once it goes, it will get a reward plus the same thing. See, if I compare both these, if I go back, q of s of a is something like this, and I will just say if you are here you will be getting this, and if you are going this, something like this. So both are equal, right? So what is the point of saying this? You people might ask, and I'm going to the next level, you'll be confused more. So see, this temporal difference is equal to r of that means after value minus this value. You can say, okay, this value is somewhat equal to this, and it will be 0, right? Yes, obviously 0. So what is the point of doing this, right? So we come to the point that every time this value will not be same. Okay, for the first time my dog will be making mistake, so it will be learning. Upon every learning, it will try to eliminate that randomness. First time it have 3 options. Suppose if it is here, it has 3 options, moving up, down, and this. If my dog moves up, it will just say, okay, I got a negative reward. It will just neglect this. So my randomness is now limited to up or down, right? So in that time, it will be somewhat neglected. It will reduce. It won't be the value equal to this. Okay, so what is the thing is, temporal difference is nothing but the value of q-learning intuition once it reached the particular state minus what was its value in this before state. Okay, so I'm bringing it to the top. Okay, uh, I have my temporal difference equation here, right? So I'm just going to use this. I have my things, right? So reward of that plus this maximum by action of the corresponding state, I'll be getting that minus the previous state, right? So I can rewrite this, right? I can just bring this here and this one here, right? So what I'm doing, see, I'm just writing Q of means Q learning of Q learning institution of a certain thing is equal to Q learning intuition of the certain point plus here we bring another term called alpha which is into T into D. Alpha is called the learning factor. Okay, we just said, right, first it will be zero learning and then it will just start off with learning. Okay, this time this move I got this learning, right? So you might be thinking, okay, this and this are same, we can just cancel out. No, so we are going to move further. So this a value, a Q learning intuition value is something equal to the previous Q learning intuition value plus alpha times of temporal difference value. Okay, so I can just implement the same here. Okay, so what I can get is Q learning intuition of a certain state is equal to Q learning intuition of its previous state plus alpha times of reward of this and this. So if my alpha is 1, I can just cancel this out, then my thing will be this. So at first time my alpha will be 1, so I can neglect these two because this will get cancelled out with this, so this will be my reminder. So at first learning or the first move or at the first triad, my Q temporal difference will be somewhat equal to the Q learning intuition of the agent. Okay, this is fine. I'll just give you some additional reading material so that you can look into that and you can just see. Okay, so this is something like learning to predict by the methods of temporal differences. Based on this, I just shown here picture, right? See, yeah, a novel is there, so it will be bad. So if I have a possibility of losing is this, winning is this. So it will, when it is in this state, it will just you by its learning, by its predicting, it will just move. Even though it is 10%, it will move. How it does, how it determines the move, how it determines the change, or how it determines this action, that will be the based on the temporal difference. Okay, so you can just do this, you can just refer this paper. I can just give the link also here, you can just find it. It was done by Richard Sutton and then year 1988, so you can find that. Okay, so next what we'll be seeing is we have our activity here. So what activity I'm just going to leave as of today is you gonna try how the reinforcement learning is occurring in a simple game. Try getting a knowledge on how a reinforcement learning is occurred in Pac-Man game. So in the next part, we'll be entirely seeing how a Pac-Man game will have a reinforcement learning for a better move. Okay, I'll just leave this as of today for you to do this activity, and tomorrow we'll be upcoming with this entire module. So the first three part was a little what to say, it is a theoretical, and the last was we are going to spend on this activity part. Okay, so hope guys, hope the session is good, and I just uh, recommend you to just get grab knowledge before moving to the next part. Okay, in the next part we'll be just doing the how reinforcement learning makes a Pac-Man game more better. Okay, so thank you guys, thank you for the session, and hope we can just move on. We'll see in the next class. Okay, thank you.